Hello students, we're now going to do another optimization problem, this one involving volume. Okay, let's read out the question. A rectangular sheet of tin plate measures 24 centimeters by 18 centimeters. Squares are cut out at each corner and the flaps turned up to form an open box. And find the maximum possible volume of such a box. Okay, so hopefully you have a picture in your mind of this sheet of tin plate. We've cut out squares from each corner. All the squares, of course, are the same size, and then you can basically fold up the sides of the box, and what you end up with is a rectangular box with no top, so an open box. Okay, here's what I'd like you to do first, is to stop the video and see if you can actually draw a diagram of what the sheet of tin looks like with the squares cut out of it. I'd also like you to add to that diagram any measurements that you know and any unknowns, any variables that you might have to add. Okay, so stop the video now and see how you go with that, and then restart. Okay, let's see how you went with that. So here's my diagram. So that was the sheet of tin, 24 centimeters from top to bottom, 18 centimeters wide. I've cut out the four corners. I don't know how big the corners have to be because the volume depends upon the size of the corners. So I've called that distance there x. That means the base of the box. In this direction, the length is going to be 24 take 2x. And the width of the box is going to be 18 take 2x. So the total width of the sheet is 18 minus x minus x. Okay, that's step number 1. Okay, now step number 2 is to come up with a formula involving x for the volume of the box. So once again, stop the video and see if you can actually come up with an expression for the volume of the box in terms of x. Okay, let's see how we went on that. So volume is length times width times height. So the length of the box is going to be 24 take 2x. The width of the box is going to be 18 take 2x, and the height of the box is going to be x. So we just put those three expressions in for L, W, and H. And notice what I've done is I've actually put the x in front because that's how we typically do this with algebra. So that's the height times the length times the width. Okay, now what we're going to have to do in the next step is differentiate this function. And unless you want to try to use a product rule on this, which I wouldn't recommend, the best thing to do now is to go and expand that to get rid of the brackets. So once again, I'll suggest you stop the video, do the expansion yourself, and then restart the video to check your answer. Okay, here's my solution to that. So basically, I just multiplied these two terms by these two terms, what I call all by all, and I ended up with that expression just there. These two terms, of course, are like terms, so we can add them together to get minus 48 minus 36 is minus 84x, and then multiply all of that through by x, and that's my expression for the volume. Okay, next step, find the derivative of that. So once again, go ahead and do that on your own, please. Stop the video and check your answer once you finish. This step, hopefully for you, is pretty straightforward. So I've ended up with 4 times 3 is 12, x squared. 84 times 2 is 168x plus 432. Set that equal to 0. And now we have to solve that equation. And it turns out that this one does not factorize very nicely. So this one has to be done using the quadratic formula. So I'll assume that you know how to do that. I won't ask you to stop the video. If you do that, you end up with, in fact, I'm going to get rid of those crosses. So I made a mistake here. Excuse me for 1 sec. Get my eraser. There we go. Get rid of that. Yeah, so it turns out you've ended up with, get that into the bin, please. You ended up with two answers. X is either 10.6 centimeters or 3.4 centimeters. Now, looking at the diagram over here, it's not possible to cut out a square of side 10.6. The longest it could be would be half of 18, which is 9, which is why we had that value, oops, that value crossed out. I better do it in red. So that means we're, at this stage, we're saying the maximum volume will be achieved if the size of X is 3.4 centimeters. Okay, moving on to the next step. Let's find out if this is actually a maximum rather than a minimum. So the easiest way to do that is to use the second derivative test. So the second derivative of this function just here is 24x take 168. And we substitute in place of x, we substitute 3.4, and we end up with negative 86.4. And because the second derivative is negative, we know that we have a maximum. So at this stage, we're assuming that we're going to get the maximum volume if we cut out squares of size 3.4 centimeters. And if we do that, the volume that we obtain is just found by substituting 3.4 into the volume formula, and we end up with a volume of 655 cubic centimeters. Now the last step is to double check or to check the endpoints, but in this case there aren't any endpoints because the domain is between 0 and 9. Because if x equals 0 means you haven't cut out any corners at all, and you've cut out a corner of size x equal 9, basically it means you don't have any height left whatsoever. So therefore there aren't any endpoints, and therefore we can say the maximum volume would be 655 cubic centimeters, and we obtained that by cutting out squares of size 3.4 centimeters. Okay, this was going to be the last video, but I've decided to do one more where we actually do have some endpoints, just to show you how you deal with that. Okay, so one more video to go.